Now I'm recording. Thank you. Okay, so if from PSAT you ask it to export the system curve, it just goes to Excel and you get a curve that looks like this. And it facilitates your plotting of this. It's nothing that you can't do by yourself. So copy from exported file, paste into the system curve from PSAT coefficients file, so you can you can paste all of this stuff in, and then it will plot it for you, or you can plot it for yourself. So yeah, this thing is, come on now. There we go. Okay. And that's just the plot of a system curve, and they put that purple dot at some desired flow rate. Looks like 1200. Yeah, up there. Requested a dot at 1268.6 feet of head. Nothing magic about that. And then, of course, you can add your pump curve. Again, you have to select points. Measure will actually fit an equation. You can put points in measure, and it will do a curve fit. And then you can take the equation and program the equation in Excel, or you can just plot the points in Excel and smooth them out. You know, either way, gets it in there. This shows what happens if you select an exponent of 2 instead of 1.9. So you see, you know, when you get out to higher flows, that's going to affects the frictional head. And so you see at 5,000 GPM on this particular plot, you see you're starting to have some divergence from the curves. At the lower flow rates, there's essentially no difference. So it's not a huge difference one way or the other. All the PSAT and the pumping stuff I have was by Don Cassida. Don had a lot of experience in working with data over the years. He came to have the opinion that 1.9 fits real world data better than 2, even though 2 is theoretically what you would use. So you can use whichever you want. You know, if you're in a plant or something, there's process factors that can affect the system curve, because some of these things actually change. You know, for example, static head variables, the gas overpressure in tanks is not going to be 100% constant, you know, because there's some sort of a pressure regulator valve on that sort of thing, and it's going to go up and down and this, that, and the other. So that will affect your static head. The level control in a tank, you know, so you got a suction tank and a discharge tank. Well, those levels move up and down. And so as they move apart, then your static head is going to change. Density, you know, if these are tanks that are outside in the environment in the summertime, that stuff may tend to be warm, out there with the sun beating on it all the time. And in the wintertime, you know, you get an old northern blow through and it's -5 degrees. You know, it's, depending on what the fluid is, I mean, you know, it could be you got to heat it to keep it from freezing, but you know, so you will have density changes over the course of some period of time. On the dynamic side, on the frictional side, you know, loss coefficient variables, well, certainly valve position. You see, when we fit this, if you've got a control valve in there that's moving, when you fit this, you pick 2 points. Well, that's for that control valve at a particular location. Well, you come in the next day and they change the control valve location, guess what? You got a different system curve. You know, every time a control valve changes position, it affects, I mean, that's why it's changing position, to affect the system curve. And then the operating point is at the point of intersection where the pump curve and the system curve go. So if you close down a control valve, you put more pressure loss in the system, so then you move up the pump curve, and that's why. because so we've changed the dynamic loss characteristic of the system. Viscosity, again, you have temperature changes, so you can have viscosity changes, and that will affect the dynamic losses in operation of the pump. I mean, if it's small changes, aren't that much, but if you get a significant change, then you know, something that has to be considered. Age, you get corrosion, you get scale, you get buildup. You know, some of these old plants, they go and something happens, they got to cut a pipe in half, and they got a 6-inch pipe, and then they cut it open, and it's got an inch, inch and a half of crud built up on the inside. So if you got an inch on either side, your 6-inch pipe is a 4-inch pipe, and then the surface is not the steel. You've got some different friction coefficient. So, and that's very common, you know, on older facilities, if it's a flow that can cause, you know, some sort of a buildup to accumulate. Sometimes they have to go in and clean that stuff out. It'll get so bad they can't use the, you know, they can't force enough fluid through it, and then they have to shut down and rinse it out, or put a pig down there, or somehow physically go in somehow, a chemical cleaning to dissolve that stuff and get it out of there, so then you can operate the system again. Filter or strainer cleanliness. Strainers are devices that the flow goes through. They have a mesh. They have like a cylinder that's made of like a mesh filter out of screening material, and the fluid has to flow through that mesh. And so any you know, particulates, anything large enough to get trapped in the mesh builds up in the strainer. And, you know, after a year or two, it's probably a good idea to, you know, I mean, they're made, you just have to valve off the flow, and they got a little bolt on them, and you undo them, and you take the cap off, and you pull the strainer out and go, oh, wow, that thing's filthy. Clean it out or put a new one in, cap it back up, and all of a sudden, guess what, man, we got 1,000 GPM. That's why we only had 700, you know, because your strainers are filthy. And the system itself, sometimes we have actually changed the piping diagram, and that will obviously change a system curve. So all those things can happen. But, you know, why is this system curve so important? Well, it's fundamental to everything that we do. And that's why in these slides we spend so much time on it, because everybody and their cousin that works with pumps know about pump curves. But like 10% of those people understand system curves, okay? And so we want to make sure that you got both sides, because the pump is only half of the story. The system is the rest of it. So the system curve is fundamental. First thing we should do in any pumping system optimization is ask whether we can either change the system curve or change where we're operating on it. And we've kind of seen that, and we'll see it some more. The real world is often significantly different from the picture painted by designers using generic loss characteristics. Okay, so that generic loss characteristics, I think we talked about this. When you look at all of the loss, all the K values for like a valve, an elbow, an expander, a reducer, an entrance, you usually see a range, 0.2 to 0.5, 1 to 3, whatever. Well, the designer is always going to pick the biggest number, because he wants to make sure that pump is big enough to deliver the desired flow when they turn it on after it gets built. And so most likely that pump's going to be oversized. And then the contractor, the contractor gets the stuff, and if you order a pump that's 20 horsepower, he's probably going to put one in that's 30 just to make sure. Because the last thing he wants is to have to come back in, rip out a pump, try to get it restocked, get some money back, buy another pump, put it back in. Oh man, that's like, no, he ain't going there. If it's too big, no problem. That's what valves are for, you know. And that's what we kind of rail against from an efficiency point of view. If you can buy it with a VFD, then you can buy the bigger pump, and then you slow it down with a VFD, and you don't incur the energy loss across the valves. So here's what you see out there. That valve, that's a gate valve. And so first of all, Gate valves are not supposed to be used for throttling, but you can't tell Tennessee or Eastman Chemical that, because I was up there a year and a half, 2 years ago doing pump stuff with them. And I mean, every throttle valve they had was a gate valve. And you go, what are you people doing? You're not supposed to do this. Well, it works for us. We've been doing it a long time. Well, the gate valve people don't like it. So, yeah, I know. When we call them and tell them this, they just rail at us. But we're not changing all these valves. And so we're going to use gate valve. Okay, use gate valve. But anyway, that's a gate valve. That's not Eastman, but it could be. They had a lot of them that look like that. And see, that's a rising stem valve. So if you look here at the top of this, and I wish this picture was a little bigger because this is the suction side. The suction side is going to be wide open because you don't want any pressure drop on the suction side of the pump that could lead to cavitation. So if you're going to throttle it, you want to throttle it on the discharge side. And see how this stem is further down than this stem? This stem probably goes clear up to here because as you turn that handle, it backs that gate off and that stem goes way up. So you can look at the stem position. You know, you get on the suction side, you're almost always going to be open. So you look at the suction side stem and you look at the discharge side stem, and if it's the same size valve and all that, you go, you can take your tape measure and say, this one is, 8 inches sticking up here. This one is 4 inches. So that thing is about in the 50% position. Then the question is, at 50% on a gate valve, how much flow do you get? Well, then you call the gate valve manufacturer and say, hey, send me a CV curve for your gate valve of CV versus position. They say, no, we don't publish it. What do you mean you don't publish it? Our valve should be either full open or shut. There's no point. They'll tell you the full open CV, but they won't tell you anything in between because they don't want you using it for that. So we were up there at Eastman doing all this stuff, and you can find a little bit of information. And they had a pretty good valve shop, and their valve shop had developed their own information to work from. So it's kind of interesting. If you see one like this, there's no point going to the manufacturer for the curve because they won't give it to you because they probably have it, but they're not going to give it to you because they don't want to encourage that sort of behavior. This is a butterfly valve, okay? And so if that handle is perpendicular to the pipe, because the flow's coming out of that's a washer. That's at Schneider Electric. They're making electrical panels, breakers and all that stuff. And so they punch all this metal and then they have to wash it before they paint it to get any oils or anything off, or the paint it won't take paint very well. So that's the parts washer. And they got 7 pumps in a row. 1, 2, 3, 4, 5, 6, 7. The first one is, hot water rinse. And the second one is detergent. And the third one is this. And the fourth one's this. And the fifth one's this. And the sixth one, the seventh one. By the time you get through, that daggum stuff's been washed and rinsed and all that stuff. And then they hang it. And then it dries on the conveyor as it's heading in. And then they paint it. You got all this, guy spraying it or robot spraying it or whatever. And then they bake it in the ovens. Okay, well, so if that handle was perpendicular to that red pipe sticking out sideways, that valve would be shut. And if that handle is parallel to the pipe, then that valve is open. So how would you estimate it? Is it 50% open? I don't think so. We said 35, 40, probably 40%, something like that is a decent. Now, that's valve position. What's it do to the flow? Well, then if you want to know what the flow is, you got to go get the CV curve and go back to the valve equation. Now, what they do for this, you see that pressure gauge up there, that there's a pump down inside there that's pumping that. So, well, actually, that pump's off to the side. You see the motor. It's like a vertical pump. And there's the shaft going in right over here. And so the motor's up here. And then it's pulling water in and pumping it up this. And it's pumping it to a bunch of spray nozzles. Well, those nozzles have a certain pressure that they want to see upstream. And that's why that pressure gauge is there. So when they turn this pump on initially, They look at that pressure gauge and go, oh, no, 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 that's too high. And that's typical because the pump's a little bit oversized. And so then they start closing that valve, and that's a pressure drop until they get the pressure that they want on this gauge, and then they lock the valve down. And it sits there in that position for the rest of its life, probably. You know, wasting energy. And so we had 7 of those in a row. Well, this was an Excel plot that they sent me because Schneider Electric makes VFDs. Not at this plant, but that's one of their product lines. So they called up their sister plant and they said, hey, send us over 7 VFDs. They probably didn't pay them anything, you know, or what, not much, not compared to what you, me, or anybody else out there would pay. So within 2 weeks, they had these VFDs installed and the valves open. So that's measured savings on these pumps. That's done by Schneider. And we put the actual measured savings in our report. That's pretty good. That's the only time that's ever happened. And probably the only time it ever will happen. But so, you know, these are different size pumps, but you can see, you know, the amount of throttling. Look, I mean, this guy was, I don't know, $1,650 a year, went down to a little about $610. That's $1,000 a year. Another $1,000, $1,100 a year. I mean, my goodness, look at that. That's what the speed control can do relative to the throttling control on valves. It's not always this good, but this was pretty ideal. And you know, Schneider Electric sells energy management services. They have a group in North Carolina, and they have people like me and, you know, some of the people that graduate from here go to work for them. And they get all trained up, and they go in plants and tell people how to save energy. And so Ed Wilhite's a friend of mine. He works in this plant. He's in administration. He invited us in, and I said, Ed, we're not going to find anything. You guys are in the business, man. What? This is going to be a waste of time. He said, oh, no, I wouldn't be so sure. So we have our little office meeting, you know, about, I don't know, 30, 40 minutes, talk about the program and all this crap we're doing. Walk out the door, and I walk out that door, and that parts washer's right there. And I'm walking right in and looking at that valve. Ever we walk out of there, and I just got done telling this guy, we're not going to find anything because you guys are Schneider Electric. I walk out the door, and I look at that, and I said, Ed, look. He said, yeah, that's the washer. Ed, look. What? The valve. Yeah, that's a butterfly valve. Ed, it's pinched. Oh, yeah. I walk out that door 15 times a day. And he's an energy guy. He never thought about it. So, I mean, you know, it's amazing the stuff that, I'll tell you a story. Y'all remember when the lights in Brown Hall, the hall lights, used to have every other one out? You remember that? Every other lamp was de-energized. Well, I was the reason that was that way. Years ago, I was working with Andy Loftus, and we were trying to come up with ideas to save energy. And so Brown Hall was our test bed for hall lighting. They're just sitting out there. You don't need every one of those lights burning to be able to see up and down and read. I mean, it was that way for 10 years. Well, so we got a new dean, Dean Slater. First time Dean Slater walks in the building, he goes, why are all those lights out? I don't like that look. I think we need to put those back. 2 days later, they got the maintenance folks from Tech coming down here putting all the light bulbs back in the hall. So Tech paid $5,000 to a guy, Steve Hutchins, who owns a company, a lighting company in Knoxville, to come in and take these all out and change them down so we could save energy. And it took the dean one walk in the building and one phone call to have it all changed back. Welcome to the world of energy management. Now, they did put LEDs in. So the dean's response was, well, we're not using any more energy because we went back with LEDs, and the LED used half as much as the fluorescent. And my response was, okay, so we could still be using half of what we are if we had just changed out every other one. Well, yeah, but I didn't like the way it looked. Okay, you're the dean. I'm not. The lights are burning. This video will probably get me fired. Y'all realize that, don't you? That's all. Okay. So, okay, here's another system. This is the condenser, oversized condenser water pump. This was up in Pennsylvania. I can't remember that. I can't pull up the company name right now. But they had two chillers. They took out one chiller, and they didn't want to change the pump. So they said, we'll just throttle it, because you can only put so much flow through a condenser on a chiller. You'll damage it. And so they throttled it. It's a little hard to see, but this, I think there's a, do I have another picture? No, I don't. That's the best picture. But there's a line right like that, and if that line was straight across, that valve would be shut. That valve was almost shut. They couldn't shut it anymore because it cavitated the valve and tore the valve up, and then they'd have to replace the valve every year. So they could only pinch this one so much. So then this is on the same line. This is at the chiller, and then they pinch this one. So this and this are both throttling the same pump. That poor little pump was throttled way back. And so that's the analysis of it. Oops. So let's see. So we did the speed measurement. This was the rated speed, 1780. I think I may have shown some of this before. This is that curve. This was the measured point, because we measured the flow and we measured the head, and it was operating here even though the speed was up here, which would indicate maybe the impeller was a little bit degraded, because you would have expected it to be on this curve, but it wasn't. So I expect it had a little bit of a maintenance issue. But at any rate, so you can see, so the way you think about this is, if we open the valve, it would go all the way out here, right? And then if we did that and then slowed it down with a VFD, then we could come down, we can operate down here, which is basically on the system curve with the valve wide open. There is another system curve up here, which I didn't draw on this slide, which includes the valves being pinched the way they were. So basically, what we can save is, we're going to have the same flow either way, but we can, instead of generating this head up here, which is, I don't know, 115 or whatever, we're going to operate down here, which is, what is it, 150, that's 50, that's 55 or whatever. So that difference in head represents the energy savings that are available by going to variable speed. And then there would be a drive loss. That VFD will have a little bit of a drive loss, which I don't think. So this was a hand calculation. In fact, last night, I'm using this example in this workshop tomorrow. So I punched all this in PSAT last night, but it's not bad to see it. I mean, this is what PSAT is basically doing for you. So the pump efficiency was about 75%, motor efficiency 95%. So, here's how we start getting to the energy. So this is the amount of energy that's dropped out of the fluid. So I estimated 63 feet. So the difference from that point to that point in this calculation is estimated at 63 feet. So there's GPM, feet ahead, specific gravity, divided by 3960. So that's basically our water horsepower. That's the energy that is dropped out of the fluid flow as a result of going across those valves. Okay, and then so I'm converting from horsepower to kW, just a conversion factor, and then you divide by the efficiencies, because this was energy that was actually taken out of the fluid. Well, where did it come from? Well, it came from the pump, and the pump's only 75% efficient, so we got to divide by 0.75, and the motor is only 95% efficient, so we got to divide by that. And so it was worth 29.6 kW of input energy into the motor that's driving the pump. Well, okay, it's 8,000 hours a year. Whoops. So that's 236,800 kilowatt hours a year at 6 cents. It's a little over 14,000 a year. Was a 75 horse motor. Estimated installed cost of the project 15. So it's about a 1-year payback to put in the drive, slow it down, and open the valves. So instead of operating up here with valves pinched, we open the valves and then we slow the pump down and we get right down here, which is a much more efficient place to operate. Okay, let's see. Let's go in this. Oh, okay. So this is some stuff that Don did at, this is at Oak Ridge someplace. It may be Y12. I'm not sure. But anyway, so here's a picture of the system. You know, he's got some of his his pressure transducers installed, and he's taken some measurements on them and all. So they went back to the plans to the design firm, and so these were the design calculations. So there's an 18-inch 90-degree elbow with a loss coefficient of 0.103. A check valve to make sure the flow doesn't go backwards when you turn the pump off or something. The loss coefficient of 2. An expander from 18, so here's an expander from 18 to 24 inches. And that's got a coefficient of 0.4. And there was supposed to be a knife gate valve that never got put in. Whoops. Yeah, contractor put a little extra, you know, that helped him buy a new pickup truck, right? He charged him for that gate valve, never put it in, and nobody caught it, you know, stuff happens. Okay, so the flow was 11,400 GPM, which is 15.7 feet per second in a pipe of 17.25 inch ID for the line. So that makes the velocity head 3.81 feet. Well, so the summation of the K's over here times the velocity head equals 10.4 feet calculated head loss at the measured flow, design flow rate for the system. Okay. Well, so here he's measuring the pressure drop across here. So this is the delta P. These are the pressures he's reading. So 54.3 minus 51.6. And then what? This is times 2.31. That's our conversion for standard water. And then if the specific gravity is different, we have to divide by the specific gravity. So the specific gravity in this case is 0.985. And so that's 6.3 feet. But the elevation difference, measuring from the location of these two pressure transducers and the direction of the flow, that's a minus 4 feet. And so then the change in velocity head from, this is 24 inches to 18, v squared over 2g, the difference between v squared over 2g at this diameter and this diameter is 3 feet. So the measured loss is 5.3 feet, which is roughly half, not quite half of the design. You see? And that's the way the world gets designed. And so that means that pump is going to have more capability than it should have, than it needs. Okay. So let's see. So here's our pump curve. Let's see, data collected during special tests. So system curve based on unthrottled test data. So if we open all the valves, we can come here, okay? Here's the design point on the system, and system highest normal flow. This is where we wind up operating. So this is the kind of stuff that you're going to find when you go out there in the real world and start strapping gauges on and taking measurements, measuring RPMs, getting pump curves and all that sort of thing. And then you got to put this together and, you know, figure out, you know, is there a project here? If this sits there all the time, is this an impeller trim? Could I trim the impeller and get us down to, you know, I mean, and the question becomes, what do we need for this system? Here's your design point. It's clear back here. Data collected, well, if I open the valves, I'm here, and this is what I'm really operating. So, you know, the idea is if I'm producing this much head with valves shut, if I could get down close to this system curve, I mean, that's someplace around 40 feet instead of up here, that's 130 feet. That's 80 to 90 feet of head that I could potentially save by making this pump smaller and opening up those valves. Okay. Let's look at some of the data that we need in order to do that. And where do we get it? Well, I think we may have seen some of this before. That's just a picture of a motor tag. But you see, so we've got, this is a 50 horse, RPM 1780. How many poles? How many poles are in this motor? No offense to Polish people, but how many Polacks have we got in this motor? I'm just joking. I love Polish people, I promise. Don't turn me into somebody, anybody. How many? 4. What's the synchronous speed? 1800. Come on, people. We've been through this before. 480 volts, that's a standard voltage that you see on a motor tag. When putting out 50 horsepower, that's in the shaft, that's not the input power, that's the brake horsepower out of the shaft. When outputting 50 horsepower, the manufacturer says this motor will turn at 1780 RPM, and if you have your input voltage at 460, your amps will be 61.1 amps. We have a service factor, 1.1. For continuous operation, we can operate at 15% over 50 horsepower and not supposedly destroy the motor. 3-phase, 60 hertz, maximum kVAR, reactive power. What, 40 degrees C, maximum ambient temperature. What is that in real degrees? I don't know, 40 times 1.8 equals this plus 32. 104 degrees Fahrenheit is the maximum environment that pump's supposed to operate in continuously. So if you're operating that thing in like an air compressor room or something, and it's 110 degrees in the summer, you're going to shorten that motor life. It's above the rated ambient. Heat kills motors. The fastest way to destroy a motor is let it operate in too warm a condition. And I don't know, so there's your nominal efficiency, 94.
What determines the temperature that you can operate at?
What determines?
Yeah.
Well, it's, I mean, the way you know is you look at the manufacturer rating. But I mean, do you want to know specifically what in the motor?
Yeah.
It makes two of us. You know, I mean, insulation, I think down is one. The insulation has a particular temperature rating, and when the insulation, that's the electrical insulation, it starts breaking down, and then you get shorts and all that sort of stuff. I mean, I'm no expert on that. You know, you could go out there and look, like, you know, specifically how does heat kill a motor, but I think the insulation is one big factor. That's a good question, Spencer. Wish I had a better answer. That may motivate me to go find one. Okay, there's another motor tag. That's a 450 horsepower. This one gives power factor, 90.5. Nominal NEMA, North American Manufacturer Association, I think. North American Electrical Manufacturer, something like that. 95.4 guarantee. See, no, the NEMA efficiency is 95.4, but the guaranteed efficiency is only 95. So they're going to be, you know, the lawyers told them to put that on there. Anyway, this is information from a pump. That's a vertical turbine pump tag. But anyway, this is what you look for. You go out there in the field and, you know, you find a nice pump tag and they painted it. They had an intern for the summer and they told him to go paint all the pumps, and they didn't tell him not to paint the tags. And so he painted everything, and you go up there and you go, well, crap, I'd like to know what model number that pump is, but some smart person has painted it, or it's corroded, or it's fallen off, or it doesn't have one, you know. There's another one. Okay, pressure flow measurements, instrument, miscellaneous. These are different types of pressure transducers. The Bourdon tube, that's the curved tube. Put pressure in, you got more surface area on the outside than the inside, so it opens up with pressure. Bellows, diaphragm, piezoresistive, all this. So that's a Bourdon tube. So you see that tube, that curved tube in there, you put pressure in there and it tends to open up, and then you got a mechanism that changes the pointer position. Practical considerations, service environment history, water hammer, not good on pressure gauges. Calibration, do we ever calibrate them? Hopefully. A big plant will have a calibration department that goes out through the instrumentation. There'll be a little sticker on it, say when it was last time it was calibrated and all that sort of thing. A smaller company, if you want to know, you better take your own gauge. And hopefully you got a handle so you can close it off, so you can take their gauge out and put your gauge in. And so then you got some confidence in the reading, because you know any of this data, if you don't have some real reason to think that the gauges are good, you got to take with a grain of salt. Instrument range, accuracy, overpressure. If it goes over pressure, does it damage it, or you know what happens? Physical location, you know, where are we connecting into the system? Does that look appropriate? Accounting for different elevation, you know, or do we look at, you know, if we're doing delta P off across the pump, you know, we got to take the elevation into consideration. Can we vent air from the system? You know, are we likely to get this thing airbound? That's another important characteristic. This is great. What do you think the system pressure? I know I'm over time. This will be one more slide. What do you think the system pressure is? So what do you think? No, what do you think? 50? I don't know. 48? What do you think it is now? It's not connected to anything. This is what happens when a gauge stays in the same pressure for 10 years, and it's never calibrated, it's never taken out, it just freezes in place. And it doesn't matter what the pressure is, it's going to read the same thing. Okay. All right, enough of this frivolity. So we'll go over the pump reading quiz next time. And so hope you guys are doing great. See you later. Bye.